You're standing right now. Feel that? Your feet pressed against the floor. You call it gravity pulling you down. But here's the thing that'll mess with your head. You've never felt gravity. Not once in your entire life. What you're feeling right now, that pressure against your feet, that's the floor pushing you pee. Not gravity pulling down, the floor pushing up. And if that sounds backwards to you, good. Because everything you think you know about gravity is about to fall apart. The moon is falling right now. Has been falling toward Earth for 4.5 billion years. Falling and falling and falling, and yet it never gets any closer. Just keeps circling up there, trapped in eternal freefall. What kind of force does that? What kind of pull pulls forever, but never actually pulls anything in? And here's the really strange part. According to Newton's equations, if you could suddenly move the Earth, the moon would feel it instantly, immediately, across Urbex scissors, ling miles of empty vacuum with no delay whatsoever. How does that work? What's the mechanism? What carries that message through the void? Newton himself couldn't answer that question. He called it action at a distance and openly admitted he had no idea how it actually worked. The math was gorgeous, the predictions were perfect, so everyone just stopped asking. But they shouldn't have stopped asking, because gravity isn't what Newton said it was. It's not even close. Gravity isn't a force at all. And once you see what it really is, once you truly understand it, you'll never look at the universe the same way again. And let's go back, way back, several centuries ago. Nobody understood how planets moved. Copernicus figured out they orbit the sun, which was revolutionary enough to get him in serious trouble. But knowing that planets orbit the sun doesn't tell you how they orbit. What paths do they follow? Are they perfect circles, spirals, something else entirely? You know, enter Tycho Brahe. This man built an entire observatory and spent decades, literally decades, recording planetary positions night after night after night, measuring angles with brass instruments to fractions of a degree. Why such obsessive precision? Because you cannot understand nature by sitting in a chair and thinking really hard. You have to look. You have to measure carefully, precisely, write down exactly what you see. That's where real science begins. In the data, in the observations, not in your assumptions about how things should work. Tycho's data eventually reached Johannes Kepler. Kepler wanted to find the true shape of planetary orbits. He tried circles first because circles are elegant, beautiful, mathematically simple. And his predictions were close, really close. But Mars was off by 8 arc minutes, 8/60ths of a degree. Most people would have called that good enough, blamed it on measurement error, moved on. But Kepler knew Tycho's work. He knew that man didn't make 8 arc minute errors. So Kepler did something that most scientists find almost impossible. He threw out his beautiful theory and started over. Sembient, after years of grinding calculations, he found it, ellipses. Planets move in ellipses with the sun at one focus. The match to Tycho's data was perfect, absolutely perfect, beautiful. But it raised a deeper question, a more troubling question. Why ellipses? What force creates that specific shape? And meanwhile, across Europe, Galileo was doing something that seemed almost childishly simple. Rolling balls down ramps. That's it. Just watching balls roll. But pay attention to what happens. Roll a ball down an incline and it speeds up. Fair enough. But then let it roll onto a flat surface. It keeps going. It doesn't stop immediately like you might expect. It rolls and rolls and rolls until friction gradually slows it down. Now here's the thought experiment that changes everything. Imagine you could eliminate all friction, every bit of it. What would happen? The ball would roll forever, same speed, same direction, forever. No force needed, no continuous push required. The motion itself is natural. An object moving in a straight line doesn't need explanation. That's the default state of existence. What needs explanation is change. Slowing down, that's friction acting. Speeding up, that's a push. Changing direction, that's a sideways force acting. This is inertia, the first law of motion. And it creates a massive puzzle. Planets should move in straight lines. That's their natural state. Straight lines through space, constant speed, no deviation. But they don't do that. They curve. Their paths bend continuously toward the sun, deviating from straightness every single instant. Something must be deflecting them constantly. But what? Isaac Newton saw it. Planets want to go straight because of inertia, but they curve. Something changes their motion. He called it gravity, universal attraction between any two masses anywhere in the universe. The force depends on two things. More mass means stronger force. Greater distance means weaker force. Specifically, the force drops off with the square of distance. Double the distance, you get 1/4 the force. Triple the distance, 1/9 the force. Simple. Elegant. Devastating in its implications. With this one principle, everything clicked into place like tumblers in a lock. Why ellipses? Because planets are falling toward the sun while simultaneously moving sideways. The combination of falling plus sideways motion creates elliptical paths. Kepler's laws, which he'd extracted through brutal calculation, emerged naturally from Newton's force law combined with inertia. Why does the moon orbit Earth? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it, tracing out a circle. Why does an apple fall from a tree? Earth attracts it, same force, same law, just different scale. And here's the beautiful part. Newton did a calculation. He figured out how much the moon falls every second, how much its path deviates from a straight line. Then he calculated how much objects fall here on Earth's surface. When he accounted for the difference in distance, the numbers matched perfectly. Revolutionary. The force pulling an apple is the exact same force holding the moon in orbit. Heaven and Earth governed by the same physics. With Newton's law, the universe made sense. Ocean tides happen because the moon pulls on Earth's water. Earth is round but bulges at the equator because it spins. Comets return on predictable schedules because they follow elliptical orbits around the sun. Strange observations that had puzzled astronomers for generations suddenly found explanations. Jupiter's moons sometimes appeared early in their predicted positions, sometimes late. Turned out light takes time to travel, and when Earth is farther from Jupiter, light takes longer to reach us. This led to measuring the speed of light for the first time in history. Manned planets wobble slightly because they pull on each other, not just on the sun. From careful measurements of wobbles in Uranus's orbit, astronomers predicted a new planet, calculated exactly where it should be, pointed their telescopes there, and found Neptune right where the math said it would be. For 2 centuries, Newton's law of gravity stood as one of the greatest achievements in human history. It explained everything anyone could measure, precise, predictive, universal, but there was one detail, one tiny nagging detail that nobody could explain. Drop a hammer and a feather in a vacuum chamber. They hit the ground at exactly the same time, precisely together. Now think about what that means. The hammer has way more mass than the feather, way more. So according to Newton's law, gravity should pull it much harder, much, much harder. But the hammer also has more inertia. It resists acceleration more. And these two effects, the stronger gravitational pull and the greater inertia, cancel perfectly. Not approximately, not close enough. Perfectly. Every object, regardless of mass, falls at exactly the same rate. Why? Newton's theory requires 2 completely different properties that mass can have. Gravitational mass determines how strongly objects attract each other. Inertial mass determines how hard it is to accelerate something. And for every substance ever tested to incredible precision, these 2 properties are always perfectly proportional. Always. Gold, lead, feathers, hydrogen, neutron stars, it doesn't matter. The ratio is always exactly the same. But why? Why should the attracting property of mass and the resisting acceleration property be perfectly equal? Newton had no answer. Just this remarkable coincidence that made the mathematics work beautifully. Or was it a coincidence at all? Then Einstein asked a different question. What if it's not a coincidence? What if that perfect equality is screaming something fundamental at us about what gravity really is? Here's his thought experiment. You're in a closed room, no windows, no way to see outside. You feel your normal weight pressing you to the floor. Question, are you sitting still on Earth's surface, or are you in a rocket in deep space accelerating upward at 4 meters per second squared? Can you tell the difference? Drop something, it falls to the floor. Same in both scenarios. Throw a ball horizontally. Curved path, same in both. Stand on a scale, same reading, same sensation. There is literally no experiment you can perform inside that room distinguish sitting still in Earth's gravity from accelerating upward in a rocket. None. If you truly cannot tell them apart, maybe, just maybe, they're the same thing. This is the equivalence principle. And here's Einstein's revolution. The idea that flips everything inside out, objects in free fall have no force acting on them whatsoever. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in the space station, none of them experience any force. Zero. They're moving naturally, following their natural paths through space. No forces, no pulls. Nothing acting on them at all. But wait, the apple is clearly falling. Yes. But what if the apple isn't accelerating at all? What if it's following the straightest possible path and it's space itself that's curved? This is Einstein's insight, and it's so profound it's almost impossible to grasp at first. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the geometry itself. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time. But space-time near Earth happens to be curved, so straight in that geometry points toward Earth's center. You, standing on the ground right now, aren't being pulled down. You're trying to follow your natural path through curved space-time, a path that leads toward Earth's center. But the ground is in your way. The ground pushes you upward, preventing you from following that natural trajectory. That pushing, that constant upward acceleration is what you feel as weight, not gravity pulling down. The ground pushing up. MD Einstein made a prediction. If gravity is really curved space-time, then light should bend too. Light has no mass. In Newton's theory, gravity shouldn't affect massless things at all. But if gravity is the curvature of space itself, then light following the straightest path through curved space must bend. During a solar eclipse, when the moon blocks the sun's glare, astronomers measured the positions of stars near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent passing near the sun's mass. Exactly as Einstein predicted. We see this all the time now. Massive galaxies bend light from more distant galaxies behind them, creating distorted images, sometimes even multiple images of the same object. Direct visual evidence that space itself curves, astronauts in orbit float around weightless, zero gravity up there, right? Wrong. Dead wrong. The gravitational field at the altitude of the International Space Station, just a couple hundred miles up, is almost as strong as here on Earth's surface. About 500 torsions as strong. So why do astronauts float? Because they're falling. The station is falling. Everything inside is falling toward Earth contact. But they're also moving sideways incredibly fast, about 30 ling miles per hour. As they fall, Earth's curved surface falls away beneath them at exactly the same rate. They keep missing the planet. They fall around Earth instead of into it. Now, and here's the key. Everything falls together at exactly the same rate. The station, the astronauts, the equipment, the water droplets, everything. So there's no relative motion, no sensation of falling, no weight, no sense of up or down. It feels exactly like floating freely in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating in empty space because they are the same thing. In free fall, no force acts on you. You're simply following the natural geometry. Think about Earth's surface. It's curved, obviously. Earth is a sphere. But standing on it, it looks flat to you. Walk in what you think is a straight line, and from space, someone watching would see you following a curve around Earth's surface. But from your perspective, you're going perfectly straight. That's what's happening with gravity, except it's not just space that's curved. It's space and time together. Space-time. 4 dimensions woven into a single fabric. And mass curves that fabric. The sun creates a deep well in space-time. Earth creates a smaller one. Even you create a tiny well, too small to measure easily with our instruments, but they're real. Actual curvature in the geometry of reality itself. Objects moving near these wells naturally follow the curves. Not because anything pulls them, because they're following the straightest possible path through curved geometry. The moon orbits Earth because it's following the natural geometry of curved space-time around Earth. That geometry makes what looks like a circle to us the straightest possible path in that curved space. Lines. When you throw a ball, it follows a parabolic arc. Not because gravity pulls it down, because it's moving through curved space-time, and the straight line in that curved geometry looks like a curve to you. You're standing right now, feeling weight. In Newton's picture, gravity pulls you down, the floor pushes you up, 2 forces balanced. In Einstein's picture, only one force acts, the floor pushing up. But if there's only one force, you should be accelerating, and you are. You're accelerating upward constantly. The natural path through space-time points toward Earth's center. That's the free fall trajectory. Flow prevents you from following it. The floor pushes you upward, deflecting you from your natural path, and you feel that as weight. And the apple hanging in a tree is also being pushed upward by the branch. When the stem breaks, the pushing stops. The apple is suddenly free to follow its natural path through curved space-time. We call that falling, but the apple isn't accelerating in Einstein's view. The apple is finally free to move naturally. You, standing on the ground, are being constantly accelerated upward by the floor. Falling is the natural state. Standing still requires force. Once you understand gravity as geometry, the universe's most extreme phenomena make perfect sense. A star is a massive ball of gas. Its mass creates a deep well in space-time. Natural paths in that curved geometry point inward. What prevents collapse? Pressure from nuclear fusion in the core, pushing outward. Balance. But when the nuclear fuel runs out, pressure drops, balance breaks, the star collapses. If it's massive enough, the collapse continues until matter compresses to incredible density. What emerges is a neutron star, nuclear matter compressed to city size. A teaspoon would weigh 1 billion tons. Clean for even more massive stars, not even neutron pressure. Stops the collapse. Space-time curves so sharply that all possible paths, every single trajectory through that geometry, leads inward. Even light cannot escape. This is a black hole, not a thing, not an object. A region where space-time curves so severely that the geometry itself traps everything inside. We can't see black holes directly, but we see their effects. Matter falling toward a black hole speeds up, heats up to millions of degrees, radiates enormous energy before disappearing across the event horizon. Detected gravitational waves, ripples in space-time itself, propagating outward when massive objects like black holes spiral together and merge. We photographed the shadow of a black hole, the region where curved space-time bends light so severely that we see darkness surrounded by a bright ring. All from one idea, mass-curved space-time. Objects follow the curves. From this single principle, everything follows. Planetary orbits, tides, The precession of Mercury's orbit, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing. Black holes, the expansion of the universe itself. The same principle explaining how your drop keys fall also explains the largest structures we observe, galaxies, clusters of galaxies, the cosmic web spanning billions of light years. Universal, elegant. The pattern in the smallest piece reveals the design of the whole. Newton's equations work beautifully for practical purposes. We use them every day to launch satellites, calculate orbits, navigate spacecraft. They're simpler than Einstein's field equations and accurate enough for almost everything. But Einstein revealed what gravity actually is, not a mysterious force reaching across empty space. The curvature of spacetime itself. Mass tells space how to curve. Curved space tells objects how to move. Julians, when you step on that scale tomorrow morning, you're not measuring a downward pull. You're measuring how hard the scale must push to prevent you from following your natural path through curved spacetime. When you watch something fall, you're seeing an object finally free to follow the geometry that mass has woven into reality's fabric. When you look up at the moon tonight, you're seeing an object following the straightest possible path through the curved space around Earth, a path that looks like a circle because space itself is curved. And gravity isn't a force, it's geometry, the shape of existence itself, molded by the presence of mass and energy. And that is far more beautiful, far more profound than any mysterious pull across empty space could ever be. That's what Feynman understood. That's what Einstein showed us. And that's what changes everything once you really see it.